Question 1a, a riding school. We have a pasture with a fence with electric wiring. Figure 1 shows a schematic. There's a high voltage supply and an electric fence with short pulses. When a horse touches the electric fence, it receives an electric shock and is startled. And question 1a is name the parts of the electric circuit that is created when a horse touches the electric shock wire. Alright, so this is part of subdomain D1, electrical systems, in the syllabus. So let's just follow. You know that a circuit current only flows through a circuit when there is a closed loop. So let's just analyze what that closed loop is. And let's start, for example, with the metal pin. So we have the metal pin, then it connects through a wire to a high voltage supply. So voltage supply. And then it will connect again through wire, which I already listed here, and to the shock, how do you call it? Schrikdraad in Dutch, but the shock wire. And the shock wire is in contact with the horse. And the horse is then, through his legs, connected to the ground or earth, if you will. And that again connects to the metal pin. Question 1b. The high voltage supply here contains a battery that is charged by a solar panel here. It also contains an electronic circuit that converts the voltage from the battery to a higher voltage. And the higher voltage is required for this electric wire. On a sunny day, the sunlight has an intensity given here. The solar panel has an area given here in square meters, efficiency of 18%. The battery says 18 volt, 35 ampere hour. This means that a voltage of 18 volt, that at this voltage, this battery can deliver 35 amperes for 1 hour. So that's what this means. Or a current of 7 ampere for 5 hours. So again, the knowledge required for this question is again in subdomain D1. And what you need is the equation for efficiency here. It's the output power divided by the input power of the solar panel. You also need to know how given power, the energy accumulates. That's given here. It's energy is the power times time. And the other, that is, I don't think it's listed here, but that is the relation between power and intensity. Intensity, as was given in the question, kilowatt per square meters, is, as you see, a power by unit area, square meters. So in order to get the power from this, you need to multiply this by this area here. And then finally, power is the potential difference, which is called U, capital U in the syllabus, times the current. So let's first determine what the energy stored in the battery is. So, because in the end, that is the energy you need to supply by the solar panel. And it's given that it can supply this kind of voltage and current for 1 hour. So we simply have that the energy, and I use this equation here, is the power, let's say 35 amperes, 18 volt, times 1 hour. Times 1, and just need to be careful for the units. And this is equal to, so this unit is volt and ampere. So this will be watts. So that is, put it in your calculator, 630 watt. And I just convert it into kilowatts, because that's kind of commonly used for like electrical appliances. So yeah, again, this is using P times T to figure out what kilowatt hour, sorry, kilowatt hour, watt hour, kilowatt hour. Right, this is a unit of energy. Watt is basically joule per second, and I multiply it by time, so I get units of energy. Again, you can also convert the hour here into seconds, and then you get something in joule. But again, this is slightly more convenient. Okay, so that's one thing. And what kind of output does this solar panel have? Well, the output power, using this equation here, the output power of the solar panel is then this efficiency times the input power. And that is 0.18%. And what is the input power? That is given here, the intensity, 0.97 kilowatt per square meters. So remember that, times 0.7 a meter squared. So this is a kilowatt per meter squared times meter squared. And that means if we multiply this, put it in the calculator. I did that already just to save some time. Then you get 0.131 kilowatt. Okay, and I kept 3 significant figures, one more than you actually need with multiplying. It's fine as well if you already round it to 2 significant digits, actually for both cases here. Okay, so now we know the total output, including taking into account efficiency, and we know the total energy. So now we just again use this equation to find the time. We divide the energy by the power. So what we get is the time is then the energy, which is 0.63 kilowatt hour divided by 0.31 kilowatt, the power. And this is 4.81 hour. And I just round it in the end to 2 significant digits, so it's 4.8 hour. Question 1c. The fence wire has a circular cross-section and is made of stainless steel, which is roestvrij staal in Dutch. Its length is 350 meters and the diameter is 2.8 millimeter. Calculate the electrical resistance of this wire. So what we use here is the equation, which is also in the same subdomain, which relates resistance R to resistivity. Rho is R times the surface area of the cross-section of the wire divided by the length of the wire. And we give the material, so you need to use the Bina's book to find that this is the resistivity of steel. That's a table which should be called properties of metals. And that's all we need. So we just right? R equals rho times L divided by A. The longer the length, the higher the resistance. So that is, plug in these numbers. The length is 350. Oh, okay, then the surface area is pi times the radius squared, which is just pi times half the diameter. So 1.4 times 10 to the power minus 3 squared. And then we just substitute this here. And I already calculated that up to two significant figures, that is 41 ohm. And again, I use two significant digits because the arguments here are given in, with that kind of accuracy. Question 1D. An installation with an electric fence wire must meet four requirements. The unloaded output voltage must not exceed 10 kV. And let me explain a little bit what is meant by unloaded output voltage. In a circuit like this with some power supply or battery supply, generally these batteries have some internal resistance. And if you put a load on this, there will be a voltage difference over the load, but also over the internal resistance. And that in generally it depends on the values. As soon as you load the power supply, voltage over the voltage difference over the load might drop because there will be a voltage difference over the internal resistance. And in a complete situation where there's no load at all, then the voltage output, there's no current, so the voltage output here is exactly the same as the voltage output of the power supply. So this one cannot exceed 10 kilovolt. Then, so they actually give it a pulse. That means like a voltage that varies over time, and it cannot exceed 10 milliseconds. The maximum current must not exceed 15 amperes at a load resistance of 100 ohm and 500 ohm. And the energy in one pulse must not exceed 6 joules. And we already saw before how much actually energy is stored in the power supply system. Manufacturer wants to market a new installation, and the voltage pulses at different load resistances are shown in figure 2. So figure 2, you see the voltage U in units of kilovolt as function of time, and for an open circuit for a load of 500 ohm and a load of 100 ohm. And again, if the load here is 100 ohm, the current will be higher, the voltage drop over the internal resistance will be higher as well. So the voltage drop over the load will be lower, as you can see here. So this is kind of pretty consistent. And kind of you can see as an ideal battery, the output is actually 8, or the maximum is actually 8 kilovolt. Let me see, where was I? So we have figure 2. And then if you measure the power, so that's the voltage times the voltage over the load times the current as function of time, then you get this curve here, figure 3. But they also say that this applies to both load resistances, 100 ohm and 500 ohm. So it doesn't matter what load resistance you use. And then finally, using these figures, show that the maximum value of Pt, E as function of t, is correct both for the load resistances of 100 ohm and also for the load resistance of 500 ohm. So for both. Okay. Well, what is the maximum power? So say P max is 40, say 40.0 kilowatt. And then we use that power is the voltage times current. This is also given in the syllabus. And using Ohm's law, that is just the voltage squared divided by the resistance, or the load resistance. What is the maximum? Well, that happens when the U is maximum. The P max, say at 100 ohm, would then be 2.0. So the 2 is significant. The O might be uncertain, so I keep 2.0 and times 10 to the power 3 volt. I need to square this and divide it by the load. So I calculate that already. Then you get 4.0 times 10 to the power 5 watt. And then you can see that this is then correct. So these two are consistent for 100 ohm. Then for 500 ohm, the maximum power. Here we say 4.5. Again, the 4 is certain, and then 0.5 is kind of an estimation. So we write it like this: squared divided by 500. And calculating this up to two significant figures, then you also find it's correct. Question 1e. For each of the four requirements, explain whether this new installation meets that requirement. Use the figures on the answer sheet to do so. So number 1, well, the unloaded output voltage must not exceed 10 kV. So let's look at the unloaded, that means open circuit, as I mentioned in the previous answer. And that is at 8 kV. So 8 kV is lower than 10 kV. So this is okay. The duration of one pulse should not exceed 10 milliseconds. Well, 0.3 milliseconds is smaller than 10. So that's okay. The maximum current must not exceed 15 amps at a load resistance of 100 ohm and a load resistance of 500 ohm. Okay, well, let's calculate the current, the maximum current. So for a given resistance, the maximum current happens, of course, when the potential difference is maximum. So for 100 ohm, that is just so the U max divided by R is, what to say, 2.0 times 10 to the power 3 volt divided by 100 ohm, and that is equal to 20 amperes. So that's actually exceeding 15 amperes. So this is not met. So back to the drawing board. Let's see what happens for 500. Then Umax is, what was it again from the previous? 4.5 times 10 to the power 3 divided by 500. I calculated that is 9 amperes. So this is okay. Yeah, so 100 ohm is not allowed then. It's just the load becomes too small. So it will exceed 20 amps. And the load in this case would be actually the resistance of the horse if it touches the wire. And then number 4 is the most tricky one. The energy in one pulse does not exceed 6 joules. So the thing is, the power, which is the energy transferred from the battery, is not constant. And actually, in most of the energy is transferred at the peak here. And so what we use, if you plot the power dissipated as function of time, you can basically partition it in small areas. And for each area, you can calculate the work, approximate it by saying, okay, that's the value of the power at that point times the width of the area. Since in this small area, it's more closely constant. So the size of this area here is the total amount of energy transferred to the load, and so that is yeah. And so to find the total amount of energy transferred during the pulse, we just need to add all these areas. In other words, the total energy transferred is the area under this, so the integral. So it's basically the integral from 0 to 0.3 over p as function of t dt. Though I think probably students don't need to be familiar with integral calculus. It's definitely better. If you just say it's the area under this, then it's fine as well. And so what you have to do, I don't do this here, but you can estimate what this area is by calculating estimating the number of squares. And what you find then, uh, I I don't want to waste time doing this here, but it's about 4.7 joule, which is okay. So area under P versus T, which is less than 6 joule. So this condition is met. Question 2a. Maria hits a tennis ball from a height of 2.1 meters in horizontal direction. The ball leaves the racket with a speed given there and then traverses a trajectory in the vertical plane. The tennis ball has the mass given here. Calculate the speed at which the ball would hit the ground if there were no air friction. Well, this is so-called projectile motion. And in these cases, you generally need to decompose everything into x component and y component. And in the y direction, you have like an accelerated motion downwards. In the horizontal direction, without air friction, you have a constant velocity. In this case, 19 meters per second. So the ball will go down and to the right at the same time. So when it hits the ground, 2.1 meters lower, it has the same horizontal velocity and it has built some vertical velocity. And it would be then the norm or the magnitude of the vector here. So the resultant vector of these two, let me draw this here, is the velocity at which it hits the ground. We have to figure out what Vy is. And one way to do this is to find out, well, how long does it take for the ball to reach the ground? And that is can be found purely from the vertical motion. And you use this kinetic equation that is given in the Binas. And for some reason, I cannot find these in the syllabus, but at least these equations you need to know. So let's define the plus direction downwards. So we get that this delta h here, and the initial velocity vertically is 0. So I get 1/2 times gt squared. Then we find that t equals 2 times delta h divided by g with a square root. And we continue here. If I substitute then the 2.1 meters and the value for the gravitational acceleration, then this is, I did that calculation, where is it? It's 0.65 seconds. That's how long it takes. Now I know the time, so it is a constant acceleration, so my v y here is just then 0, the initial velocity, plus the gravitational constant times this time. So 9.81 times 0.65, which is 6.4 meters per second. So now I have both components and I use Pythagoras to find the magnitude of this vector. So I get, let's call this, can this call it phi, say phi final. I'm calculating the magnitude of this. They're not asking for the direction. They just calculate the speed, which is the magnitude of that. So I get v final is the square root of 19 squared for the horizontal direction plus 6.4 squared. And if you do this correctly, you find 20 meters per second. Now there are two comments to make. One is you can eliminate t from these two equations to get a kinematic relation in the vertical direction, and that Vy squared is V0 squared plus 2 times the acceleration times the kind of total displacement. And this gives you the Vy a little bit more directly. For some reason, I don't see this equation even in Binas, so, but if you use this, it's fine as well. And then, secondly, another very convenient way to work on these things is to use conservation of energy. So when right after the ball is hit, it has higher potential energy than when it is down, but the total potential, gravitational potential energy and kinetic energy is conserved. So you can say that the initial kinetic energy here of the ball, just from its horizontal velocity, plus its potential energy, has to be equal to the final kinetic energy when it hits the ground. So then this is ground level, plus the potential energy here, which we just can arbitrarily set 0. So then you get an equation like this. The kinetic energy is 1/2 m times the norm squared of this vector. And then the potential energy compared to ground, where it is 0, is just the mass times g times the height difference. And this has to be equal to 1/2 m times the norm of this final vector velocity when it reaches the ground. But the math will work out exactly the same and you should get the same answer. Question 2b. Mario wants to practice at home, even if no one is there to hit the ball back. She attaches the ball to an elastic band here. The other end of the rubber band is attached to a point K of a heavy block of lead. The block is shaped with a large round coin with a height of 5.0 millimeter. It has a mass of 4.5 kilogram. Situation is shown schematically in figure 1. So we know the thickness, let's call that T, is 5 millimeter, 5.0 times 10 to the power minus 3 meter. So that's 1. But what about the diameter? It's not given here at all, but we know that we know its mass and we know it is lead. So we use this equation for density, which is part of domain E, radiation and matter, to find out what the volume is. And it is a cylindrical shaped object. So we know that the volume of a cylinder, this is like a very flat cylinder, is pi r squared times the thickness. So the radius is, we bring pi t and the thickness t to the other side, is then the square root of the volume of the cylinder times pi t. Now, what's the volume of the cylinder? So the volume of the cylinder is just the density, no, the mass divided by the density, which is 4.5 kg divided by the density of lead. So you have to look this up in Binas. It's 11.3 times 10 to the power 3 kg per meter cubed. I did the calculation. 3.98 times 10 to the power minus 4 meter cubed. Okay, so now we have everything to determine the radius in this kind of indirect way. So the radius then is the square root of this number divided by pi times the thickness. And if you do this correctly and to the right number of significant figures, it is 0.16 meter. So then what's the, say, the proportion? Uh, well, okay, so first the diameter is then 0.32 meter. Then the diameter divided by the thickness is 0.32 divided by 5.0 times 10 to the power minus 3. And if you calculate this, you get 64. So you can indeed say that diameter is much larger than the thickness. Question 2c. So we have this elastic, and when the elastic is not stretched, it has a length of 4.6 meters. With this elastic, the elastic force is directly proportional to stretching. This is a known equation also in the subdomain about forces. It's equation here. The elastic force is a constant times the kind of displacement or times the stretch or even compression, although in the case of elastic, it is the stretch. And the spring constant there in that equation is 0.85 Newton per meter. And we can ignore the mass of the elastic. Then we say that the block must remain in place all the time. And at a given stroke, the maximum stretch happens to be 9.9 meters. And the elastic then makes an angle of 40 degrees with the horizontal plane, which is shown here in figure 1. Then calculate the minimum friction force between the block and the floor so that the block will not slide. Okay, so we have this situation. We have a point K here and the elastic on an angle of 40 degrees, and the stretch is 9.9 minus 4.6 meter, which is 5.3 meter. And so the elastic puts a force on the ball and the on both ends actually, K and the ball. So you have this situation sketched here, and in order to figure out what the horizontal component is, because only the friction only has to compensate for the horizontal component of the force. For the vertical component is actually the mass of the block. So we need to figure out this, and the friction force has to be big enough, has to be at least as big as this force. So what is this force Fe? Well, it is the spring constant 0.85 times 5.3, which is the stretch, and that force then happens to be 4.5 times 10 to the power 5 Newton. So the this 4.5. Yeah, this is the stretch is meters. 4.5 Newton. 4.5 Newton. And then decomposing it in the x direction, you just get your 4.5 Newton times the cosine of 40 degrees, which is 3.5 Newton. Question 2D. In the remainder, we neglect the signal of the block. On a subsequent stroke, Mario hits the ball away from point P at 1 meter vertically above point K. P, the trajectory of the ball makes an angle of 45 degrees with the horizontal line. The situation is shown schematically in figure 2. Okay. And in figure 3, the trajectory is drawn along the x-axis, the horizontal distance from ball K, from the ball to K. So point K is here. This is the horizontal distance. And then the vertical distance is the height relative to ground. And at point R, it hits the ground. I mentioned already the origin is point K. And this figure without millimeter division is also in the answer sheet. At a certain moment, the ball is in a point Q of the trajectory. 3 forces are then acting on the ball. Then draw the direction of each of these forces and write the name of the forces for each direction. You do not need to indicate the magnitude of the forces with their correct ratios to each other. Okay, so the ball is in an elastic. So first of all, we can, the elastic comes from point K. So if I draw this line here, again, the elastic force is some constant times the the stretch, and it's towards the point K, which is the other end of the elastic. So you have a force. I'm using red color. I don't think you can use red color in your exams, by the way. But just to get some contrast. So this is Fe. So Fe is the elastic force. Then it will experience gravity, which obviously is downwards. This is Fg. Fg is gravity. And the direction is shown here. And then the only other possible force is the air resistance, which is opposite of the velocity vector. Velocity vector is along the curve here. So I need to kind of along the tangent here of this curve. That will be the air resistance or drag force sometimes. Okay, question 2e. Determine the potential energy due to gravity and elastic force possessed by the ball and elastic at point Q. Give the answer in 2 significant figures. Sure. So one equation we need to use here is the potential energy related to the elastic force, or generally the kind of restoring force in harmonic motion. And that is given in subdomain C2. You see here E elastic is 1/2 C U squared. And U here is for the Dutch uitwijking, which means kind of displacement. And C is again this spring constant, which was given somewhere here, 0.85 Newton per meter. And the gravitational potential energy, we compare it to ground level here, is also pretty straightforward actually. So let's do that. We get E elastic is just 1/2 C U squared. And okay, the only complication here is that you need to figure out what this uh, displacement is. So what we need to do is find I think it was in the previous question, find the length here of this, the length of the elastic. And for this, we can use Pythagoras. Here we know the x component and we know the y component, so we just need to sum them and take the square root. And you can put that on your answer sheet very clearly. So what is u? Well, if you do this, you'll find that u, and I did this already, oh, it's 4.9 squared plus 6.0 squared and the square root, and that is equal to 7.8 meter. And we also know that the natural, well, without any loading, without any force, the natural length was equal to 4.6 meters. So actually, this is not the displacement from equilibrium. This is the total length. So then we find that the displacement is then 7.8 minus 4.6 is then 3.2 meter. And then we just substitute this and we find E elastic is 1/2 0.85, that's the spring constant, times 3.2 squared. And again, keeping two significant figures, this is 4.2 joule. And that's the potential energy stored in that system. And then the gravitational potential energy is just the mass of the ball times g times the height here. And that is 56 grams times 9.81 times 4.9. So calculated that, and that's 2.7 joule. And this is really what they want to know. Question 3a. Sometimes motorists can see cars approaching reflected in a road surface. Like here, the viewer here, you can see the reflection of the white car here in the road. And this is called a mirage. Can occur when there's a layer of hot air above the road surface. The refractive index of cold air is different from that of hot air, so that total reflection can occur at the interface. Figure 2 shows this situation. Here we see the viewer, the guy that took the camera here, and here we see the oncoming car. And you see that light rays are reflected in this hot layer of air. And what do they say more? There's total reflection, as for example also happens with an optical fiber. Then the question is the refractive index of hot air smaller or larger than that of cold air? Explain your answer, the 8 of figure 2. So for this question, it falls back to the syllabus somewhere hidden in subdomain E1, where they talk about critical angle and also Snell's law. So this is summarized here. If you have an interface between two mediums, I and R, and the index incident angle is related to the refracted angle by Snell's law here. This is the way I prefer to remember it, because it's Ni times sine I is Nr times sine R. Easy to remember. Now the critical angle happens when the sine of R is equal to 1. So R is 90. And remember, it's the angle with respect to the normal to the interface. So the critical angle happens when sine R is 1. That means the sine of the critical angle is NR divided by NI. And this, of course, only happens when the refractive index of the incident medium is larger than that of the refracted medium. So the second medium here. And then if this angle, incident angle, is larger, further away from the normal than this critical angle, then you get also total reflection. So that enables to answer this. So since from this, it just, well, we can immediately tell that the N of hot air because you go from cold air to hot air. So just to follow what's written down here, the N of cold air is larger than that of hot air, and that allows internal reflection to happen if there's certain condition for the angle. So the angle with the normal has to be larger than the critical angle. Question 3b. In figure 2, in addition to point L, points A and B are also drawn. For a ray of light from either point, the angle of incidence is exactly equal to the critical angle. The figure is not to scale. Explain for which point A or B this is true. Well, let's assume it's true for point A. The incident angle of point A is actually larger than that of point L. It's further from normal. But for IL we have internal reflection. So that means IL has to be larger than the critical angle. But we just said that so that means since the incident angle of A should be larger than L, should be larger than C, that incident angle from point A is larger than the critical angle. So A can actually not be the critical angle. So A is not the critical angle. And as you can see, the incident angle for L is larger than that of B. So that's consistent. That's consistent with IB being the critical angle. Question 3c. If the angle of incidence is exactly equal to the critical angle C, then angle alpha in figure 2 is the maximum angle of vision at which you can still see the mirage. So I think they mean that if this angle of L is the critical angle, then if the angle is larger than alpha, it means that the incident angle was smaller, because the incident angle, the angle of the normal, is the complement of the angle alpha here. So there is no total reflection anymore. The light is just refracting. So that makes sense, that angle alpha is the maximum angle of vision. So then they say, since the refractive index for the transition from cold air to warm air depends on the temperature difference, makes sense, angle alpha also depends on delta T. This relationship is shown in figure 3. The temperature of cold air is 20 degrees Celsius. Calculate the maximum angle of view alpha in 2 significant figures. Determine the temperature of the hot air using this angle. All right, so the sign of the critical angle in this situation is 9 is 496. Then you find, and I've done that calculation, that the critical angle is 89.488 degrees. Kept here actually 5 significant figures. And that means that the angle alpha from figure 2, so this is alpha, but this is the incident angle. Then alpha is 90 minus 89.488 equals 0.512 degrees. And now look at the graph. At 0.51, we're actually at delta T equals 50 degrees Celsius. So this in 2 significant figures, so I should give this answer, 2 significant figures. Then delta T is 50 degrees, so that means the hot air is at 20 plus 50 is 70 degrees Celsius. Air reflections can also occur over a very cold surface. In the picture in figure 4, you see a mirage of a ship. You see the ship on the water, but also mirrored hanging in the air. Explain how it is that the reflection of the ship can be seen in the sky. Okay, so let's try to draw this. So we have the seawater, and let's assume the seawater is cold, and there is like a layer of cold air, and a layer of a warmer air. And then similarly, we can have, because we saw that the N of cold. Go back to the previous one. The index of refraction of cold air is larger than that of hot air. And as we saw, that means that at certain angles, internal, total internal reflection will happen. Could happen for certain angles. We have, say, an object here, and means it's reflected here. So for an observer here, it just looks that this, whatever this is, say the ship, will will look like being hanging in air, as they mentioned. Question 4 is about a spectrometer. Certain types of mass spectrometer can be used to determine energy levels of ions. In such a spectrometer, there is a long field-free space between the acceleration part and the deflection part. So this is the acceleration part, and here you can see the ions are deflected. In these three parts, there is vacuum. The opening in electrodes P and Q, and so they're here, these openings here, and the opening R here, in the deflection part are narrow. The ion source of the spectrometer has a volume of 100 centimeter cubed. This source contains nitrogen gas N2. Its molecules consist of two atoms of 14N. So 14 is the mass number. Before the nitrogen molecules are ionized, the temperature in the source is 60 degrees and the pressure is 250 Pascal. Calculate the number of moles of N2 in the source at that time. Well, for this, we use the knowledge in subdomain E1. And here you see what's called the ideal gas law, which I wrote down here as well. And the N here is the numbers of moles in the ideal gas. And R is a constant which you can find in the Binaz book. So then we just can isolate N. So N is then equal to the pressure times the volume divided by the temperature and the gas constant R. And by this gas constant R is also related to the total energy contained in the gas at a certain temperature. See that the total kinetic energy in the gas is 3/2 times R times the temperature. That's the energy per mole of gas. Although that is that is definitely not required in this question. Okay, so we have everything here. That's actually straightforward 4 points, I would say. So we have 100 centimeter cubed, so that is 100 times 10 to the power minus 2 cubed. And just be careful with the temperature. This is the absolute temperature in Kelvin. So that is 270, remember that, plus 60 above. 270 is the 0 degrees Celsius. And then times the constant R, which is in Binaz under the in my version in table 7, under constants of nature, and that is 8.31. And just use the normal SI units for everything, then this will become a unit of mole of gas. And round it to two significant figures, you get, I did the calculation already, you get this amount of moles of gas. Question 4b. The nitrogen molecules are ionized only once to form nitrogen ions. And ionization, remember, means that an electron is kicked out, in this case from this whole molecule, and it gets a charge of 1e. E is the elementary charge. That is also found in Venus, but best to remember, it's 1.6 times 10 to the power minus 19 Coulomb. This is the charge it gets. Now these pass through the opening in P at a negligible speed, after which they pass through the electric field between P and Q. The ions passing through the opening in Q have a velocity given here, and this velocity is directed along the drawn path from Q to R, so they move here to the right towards R. The mass of a nitrogen ion is given here. Calculate the voltage difference between electrodes P and Q. Well, here we need to apply our know-how from subdomain D2 in the syllabus. And there you can find that the change in potential energy, actually the decrease in potential energy is converted, in this case, converted into the kinetic energy of the ion, and it's given by Q times the potential difference. Remember that the change in potential energy is Q times the potential difference. And this is actually the definition of potential difference. It's, remember, it has the units of Joule divided by Coulomb. So this, as I mentioned, this decrease in potential energy will be converted into the kinetic energy of the ion in this case, or in other cases when this is over a resistor, it could be converted into heat or other forms of energy, like maybe even light when it's a diode. So that means that we can get an equation for the kinetic energy in terms of Q times the potential difference. Okay. And the kinetic energy is given by 1/2 the mass of this ion times the speed squared. And again, assume that everything is converted in this kinetic energy here. So now we can just indirectly figure out, well, we know what its kinetic energy is. We know the charge of the ion. So these are all given. This is given, and this is given. So then we just very easily find what the potential difference must have been. So that is the mass of the ion times the speed squared divided by 2 times the charge. And now we just substitute what we know. And the speed, 2.9 times 10 to the power 5, square that, and 2 times the elementary charge given here. And I've done that already. That's 1.2 times 10 to the power 4 volt. Question 4c. Some of these ions are in a higher energy state, and they can spontaneously fall back into the ground state. The energy thereby released is then used to disintegrate the N2 plus ion into an M plus ion and an N atom. The kinetic energy of these two particles together is then 0.73 eV more than the kinetic energy of the N2 plus ion before disintegration. This energy is distributed equally between the two particles. An N plus ion and an N atom have nearly equal mass. Okay, so it's then something like this. We have a N2 plus ion that is in a higher, so some of these are in higher energy state. So in somehow it's in an say excited state. And then they say it can fall back to the ground state. So that will be N2 plus, say, ground state. But some of the energy then has to be released. So this, say, this is plus energy. And then this energy can be used to basically split this molecule into a nitrogen plus ion plus just a neutral nitrogen atom, and then also plus energy. And that energy is could be the kinetic energy here of these two ions. And that's actually given here. Together, these have a kinetic energy of 0.73 eV. Oh, and remember eV, that is explained in the syllabus. eV is 1 eV is basically 1.6 times 10 to the power minus 19. Okay, space joule. It's the energy acquired by a unit charge when it's accelerated over 1 volt. Okay, but so this is the total kinetic energy. So each of these will acquire about 1/2. So you can say that the kinetic energy of the N plus will be 0.73 divided by 2 is 0.365 eV. And the velocity is u, so this has to be equal to 1/2 the mass of that, the N plus ion, times or times what they call u, and then the square. So this means that the velocity has to be this kinetic energy N plus ion times 2 divided by the mass. Okay. I probably should use some better symbols here because it's a little bit messy. So this is then 2 times 0.365, and we want to convert this into joules. Definitely would be a mistake if you wouldn't do that. Then this will have a very weird unit. This has to be joules. So need to multiply this by 1.6 times 10 to the power minus 19. And what is the mass here of the ion? Well, they said that the N plus ion and the N atom have nearly the equal mass. So that is just 1/2 times 4.65 times 10 to the power minus 26 kg. Then the square root, the thing. And I've done that. It's 2 point, how many? Keep two significant digits. It's 2.2 times 10 to the power 3 meters per second. Question 4D. Moreover, it's known that the amount of energy released when an atom and an N plus ion are bonded to form an N2 plus ion in the ground state is 0.44 eV. So that means that this is the decrease in potential energy when this bond is formed. In other words, this is the energy, 0.44 eV is the energy you need to supply to the N2 plus in ground state to split it into a like ion and an atom here. So copied here from the previous page what happened. This ground state nitrogen 2, a nitrogen atom, sorry, nitrogen molecule, the ionized nitrogen molecule in its ground state had this energy, and let's call this energy delta E. That was the energy that was freed when it went from an excited state into the ground state. Now, they are asking what this energy is, the energy between this higher state and the ground state. Now we know that from this energy, 0.44 eV is needed to split or unbond the molecule into this ion here, nitrogen ion and the nitrogen atom. But we also know that there was still a remainder of 0.73 eV that went into the kinetic energy of these two. So this was still left. So delta E, and then what is used to unbond it, should be equal to 0.73 eV. So the total energy that was here to unbond it and to supply the kinetic energy must have been 1.17 eV, and that is also equal to then the energy difference between this excited state and the ground state. Question 4e. When an N2 ion, which is in the said higher energy state, disintegrates in the field free space, the velocity of the formed N plus ion is the resultant of the velocity directed along QR of 2.9, given here. This is the velocity of the N plus ion after acceleration. And the direction of u is actually arbitrary. When this N plus splits into, if this N2 plus splits into N plus, this velocity can be in any direction. Explain there are only two velocities u at which the N plus ions can pass opening R. Well, this u factor can be any direction. So let's take this direction as an example. if I add these two factors, I get a resultant factor um, that is a factor that's not pointing at R. So in this case, this n plus ion will not reach the detector here. Now this is not entirely on scale because this velocity is much faster, higher than the velocity of this ion. But still, given that this is a long distance, the only way that this n plus ion can reach R would be if u is exactly in the direction of the velocity of the n2 plus or opposite of the velocity of n2 plus. So these are actually the two only options. Question for F. In the decay, the determination of difference between these two velocities is possible only if enough n2 plus ions decay in the field free space for a measurable amount of n plus ions to pass the opening R. So I guess they want to measure these velocities of the n plus ions by deflecting these things in the, what was it called, the deflection part. So they need to have enough of them. In the decay of higher energy states, the concept of half-life is defined in the same way as the concept of half-life in decay of radioactive nuclei. The half-life of the higher energy state considered here is 2 times 10 to the power minus 6 seconds. And the total trajectory, QR, is, or the time for the N2 plus ions to cover it is 5.1 times 10 to the power minus 6 seconds. Then calculate the percentage of N2 plus ions which enter the field-free space at Q and decay between Q and R. So the equation here to use and the knowledge is in related to decay is in subdomain B2. Here you can find both equations for decay, and this is the number of basically decaying atoms. So how many kind of radioactive atoms are still there as function of time. And there's another equation here related to the activity itself. That is how many decays happen per second. But that's not being asked now. Still should know about it. All right, so then, so as percentage of the N2 plus ions that actually reached the starting point, Q. So we just need to know what is N as function of T at that point. Let me put it in this way. T equals 5.1 times 10 to the power minus 6 second divided by the number at t is 0. That's what they're asking. So that's just 1/2 then to the power 5.1 times 10 to the power minus 6 divided by the half-life, which is 2.0 times 10 to the power minus 6. Okay, so 1/2 to this power. And if you do this correct, then you find that this is 0.17 to two significant figures. So that corresponds to 17%. 70% is basically remaining. But they are actually asking how many, what are they calculating? The percentage of ions that enter and decay. So that means that 83% of the N2 plus ions must have decayed. Well, into N plus N. Question 5a. Gamma radiation has a much greater penetrating power than alpha and beta radiation. Moreover, gamma radiation cannot be shielded completely. Something always gets through the shielding. To determine the half depth of aluminum for gamma radiation, plates of aluminum of equal thickness are stacked between a gamma source and a counting tube, illustrated here. The amount of radiation measured without plates is called 100%. Through one plate, 96% of radiation is measured. Thus the plate has absorbed 4%. Explain whether the absorption of the stack of 5 plates is smaller, equal, or larger than 20%. So one thing about half depth, that is also in subdomain B2. And the equation is actually very similar to decay. It's, again, a exponential function, 1/2 to the power of the depth divided by a constant called the half depth. And this can be found for different materials in BINAS. Okay. All right, so it goes through 5 plates. So each plate lets through 96%. So 5 plates then would let through 0.96 to the power 5. They basically accumulate in this way. And calculated this is 0.815, so which corresponds to 81.5%, of course. So how much is absorbed? Well, 17.5%. Well, you actually need to round it to 2 significant figures, so say 18% to be precise, but it's no matter what, it's less than 20% is absorbed. Question 5b. The value of the half-value thickness of this gamma radiation with an energy of 1 MeV can be found in BINAS table 28. This table shows that not all substances absorb gamma radiation equally. That's actually the equation listed here. It depends on this constant d1/2 here, which can be found in BINAS. Then this absorption process is shown here in figure 2. There's a beam of photons falling on a plate, and if it encounters an electron, it disappears from the beam and is absorbed. So it will interact with an electron. Thus, with greater electron density, more gamma photons are absorbed. That would make sense. And then there is this formula for this. It is there's this formula for the density of electrons. It's rho times Z times MA, where N is the electron density, rho is the density of the material, C is the atomic number, and Ma is the mass of the atom in kilogram. And using Formula 1 determine the SI unit of Ne. Okay, well, the unit of rho is density, so that's kg divided by meter cubed. Just use this equation. It's mass divided by volume. Now C is dimensionless. It's just the count of protons in the atoms of the material. And then, well, the unit of mass is kg. So plugging this all in, we get for the unit of Ne that it should be kg divided by meter cubed, then times 1 over kg from the division by Ma. So it's dropped, so it is just meters to the power minus 3, 1 over meters cubed. Question 5c. The relationship between the half value thickness d, 1/2 of the material, and the electron density n is given by this formula, where sigma is the effective area of impact of the electrons in the material. So calculate the effective area of impact, sigma, of the electrons in aluminum for gamma photons of 1 MeV. 1 MeV. 1 mega EV. And remember, 1 EV is 1.6 times 10 to the power minus 19 joule. Okay, well, how do we find sigma from this? We know the material is aluminum, and we also know the energy of the gamma photons. So let's first figure out what d1/2 is. If we know d1/2, and we also have an equation for the electron density in aluminum that we use. We pull this up a little bit. We can use this equation. We know the density of aluminum. We know the Z value. We know the mass. And if we know d1/2 and if we know Ne, we can figure out what sigma is. Okay, so first, what is this half value thickness? d1/2. So let's go to Venus. And this is in the, let me see, in table 28. In Dutch is called halveringsdikten. What is it? F. I assume that in the English version it might be the same table or not necessarily. Actually, I don't know. So the energy of gamma, the gamma radiation is 1 MeV. That's the energy of the photons that are part of this radiation. So for aluminum, it's 4.2 MeV. Sorry, not MeV. It's 4.2. You see, what do they say about the unit here? Okay, in centimeters. 4.2 centimeters. So Venus tells us it's 4.2 centimeter. All right, we have that. Now we go back to figuring out what the electron density is. So we need to know rho of aluminum. So we need to know rho. We also need to know the mass. So let's go to the table of contents. Properties of vaststoffen. There's also one on metals. Properties of metals. And here we have aluminum that has where is it? Oh, the first column actually. Density 2.7. And the unit is 10 to the power 3 kg per meter cubed, which is good. And now, finally, what is the mass? So let's go to I think it's in isotopes. Here you can see this is kind of almost a periodic system of elements, but in like a table format. Let's find aluminum. Yeah, by the way, we also need to know Z, but no, it's 13, it has 13 protons. Then this is how much it comes in nature, and it's 100%. It is of atomic mass 26.982 units of the atomic mass unit U. Which is given here 1.66. I keep 3 here. 10 to the power minus 27. Okay, now we have everything, and let's put it in 3 significant digits. Actually, the end result should be in 2, but actually it doesn't matter. Let's keep this to 3, so this is equal to 27.0 U. Okay, that's all we need to know from Pinos. Then going back to the question, what I just was saying in words, let's put an equation to that. So we isolate sigma. So sigma is then log 2 divided by the 1/2 times Ne. And Ne, let's calculate Ne, is rho from the equation here on top. You can just see it here. C divided by the mass. So that is 2.7 times 10 to the power 3 times 13 divided by 27.0 times 1.66 times 10 to the power minus 27. So if you calculate this, you should get 7.83 times 10 to the power minus 29. Again, I just did the calculations already, or used the answering sheet just to make the videos a little bit shorter. So we already know the unit is meters or 1 over meters cubed. Okay, so this is how we calculate Ne, the electron density. So now we just all plug this in. D1/2, so that is 4.2 times 10 to the power minus meter, and times this number. And if you do this, you get 2.1, one significant digit, times 10 to the power minus 29 meters squared. And the unit has to be meter squared, actually, because this is kind of an effective area. You can also just look at what was our equation, sigma. This D has unit of meter, and we saw this Ne has units of meters to the power minus 3. So you get in this denominator meters to the power minus 2. So sigma becomes meters to the power 2. All right, 5e. To check whether the value of electron density Ne is in different materials is the same or not, the graph in figure 3 was drawn. In it, D1/2 for gamma photons of a given energy is plotted against 1 over Ne. A straight line is drawn through the points. All right, so what does that mean? It means that D1/2 is basically a constant, some constant, times 1 over Ne. So, so as the electron density increases, the depth becomes smaller. It will make sense. There will be a higher probability for gamma photons to find a kind of semi-free electron. So we also know that sigma is proportional from here, actually from the equation in the previous. That sigma is proportional to 1 over D1/2 times Ne. But now I can just substitute D1/2 here from the graph. Then it's just proportional to 1 times 1 C over Ne times Ne, and that is just 1 over C. So it's proportional to a constant. So it doesn't depend on D1/2 at all. So yeah, it means I'm for material with a larger D1/2, your electron density is lower, and in this equation, basically they cancel each other. So 1 and 2 are both incorrect, so 3 sigma remains the same. So 3 is the right answer.